friend whom I've had for a very long time. So Andre and I didn't consult before we prepared our talks, but we have a very similar start. The middle has changed. The speaker is always in the middle, but no, I'm sorry. So this talk is not about included versus excluded middle. Middles are going to be very important, but the middle is the midpoint. The middle is going to be a dissection between the two endpoints. Anyway, this was taken in I think 2009 when. So at the time I was still based in Edinburgh, and Martin and I were both visiting Slovenia at the same time. I think Martin was the external examiner for Davorin Leshnik's PhD at this time. So it's a relatively old photo, but Martin and I go back much further than that. So I actually clearly remember the day that I met Martin. It was in 1997 when he came for a job interview in Edinburgh as a lecturer, and he gave a very nice interview talk, I think, about injective spaces. And after his interview, we got chatting, and we hit it off immediately. So much so that before he so he got the job, obviously, and before he arrived as a lecturer, we'd exchanged several emails already. Martin had told me he likes to think of compact spaces as spaces for which one can compute the universal quantifier. That was already in an exchange of emails at that time. When he arrived in Edinburgh in, I guess, September or October 1997, we immediately struck up a very good friendship, and so he was in Scotland for 3 years, 2 years in Edinburgh and one year in St Andrews, and he and his wife Danielle were very nice, and so with every weekend we would kind of meet on Friday evenings, and for some reason they always invited me and my girlfriend at the time to their house, and we used to have really nice really nice time together and then once they moved to St Andrews, I used to visit them at the weekends. It was very productive time intellectually. I think it's also a very important time for Martin personally, because he and Danielle arrived in Edinburgh with no children and left with 2. Left Scotland with 2. I mean, the period in Scotland was 3 years. Martin's second son, Matthias, was born in St Andrews, as I remember. So Christopher Townsend yesterday was talking about how he and Martin used to share an office at Imperial College. I can't quite compete with that, but Martin and I used to share an office wall in that I was in room 2604 in James Clerk Maxwell building, and Martin was in room 2606. And in between us in numbers was John Longley in 2605. He was across the corridor because it was like evens on one side and odds on the other. And the wall that our offices shared had Martin's blackboard on the other side. So he was a frenetic blackboard writer. So I got used to doing my own work to the sound effects of Martin writing on the blackboard, the other side of the wall. Okay, so anyway, this is the talk's about Martin's interval in Scotland. So one interval is this temporal one from 1997 to 2000. In order to tie it in with the remainder of the talk, I want that to be a closed interval. So there's a little issue here, because at the point that Martin left Scotland, so there's a kind of border dispute potentially between Scotland and England, and in order for Martin's time in Scotland to be a closed interval, the border dispute needs to be resolved in favour of Scotland. I mean, many wars historically have been fought between England and Scotland, but I don't think over who claims the actual, whether. So actually, anyway, there's a connection to be made maybe with Peter de Beer's talk yesterday. So he at I guess. Oh dear, what's the word I'm trying to think of? He was at a cosmological level talking about whether the universe is open or closed, but I think at a smaller scale level of a country like Scotland, these things can be decided more easily by political fiat. So we're going to decide that Scotland is closed for the purposes of this talk. And just to say, because I wanted an opportunity to bring in our good mutual friend, John Longley, the assumption that Scotland being closed is not original to this talk. I first heard that made in a lab lunch talk, in an LFCS lab lunch talk in, I think, about 1993 by John Longley. That was called Munro Bagging in the Effective Topos. It was a very nice talk. If anyone wants to know what John talked about in that talk, I'd be happy to talk to you about it at lunch. Or something, but it's I wanted to bring this up because it's sort of indicative of the John Longley's extremely fertile and creative mind. So a little distraction from the main topic of this talk. So yesterday, Giovanni Sambin was promoting his own book in his talk, which you might want to buy to read. But Christmas is coming. And for Christmas, you probably want some lighter, more, well, a lighter, entertaining, but still very stimulating book to read. And John, so one of the things he's done in recent years is he's written a novel called Castles in the Air. And if you haven't heard of this book, Google it with John Longley. And I strongly recommend that as a good Christmas read. It's about the foundations of mathematics, but with a story behind it. So, sorry, so that's a little advertising spot, but this is for Christmas, and then for New Year, you can make a New Year's resolution to read Giovanni Sambin's book.
Which foundation?
So,
which foundation is it?
All, yeah, buy the book. Anyway, let's carry on with the talk. So the talk is Martín's interval in Scotland. We've already talked about Martín's temporal interval. The main subject of the talk is Martín's mathematical interval that he brought to Scotland. So one of the early things we talked about in 1997 in their flat, in Martín and Danielle's flat in Edinburgh, was Martín said, he was intrigued by how one can characterize the real numbers or an interval of real numbers in a nice abstract mathematical way that would work category theoretically in a wide number of scenarios. And there was an attempt at this by, is it Dennis Higgs or by Higgs, and who had some axiomatization of the non-negative reals that involved an infinite sum operation. But the problem is with an infinite sum operation is if you interpret it either topologically or computably, it's not compatible with the usual topology on the real numbers or the usual computability structure on the real numbers. And what Martín had realized was if one restricts to a closed interval and instead of a sum operation, one looks at an infinitary operation called which we called iterated midpoint, then those issues go away. So Martín basically presented these axioms to me. So capital M is an infinitary operation. I is the closed interval here. It doesn't need to be the closed interval from 1997 to 2000 anymore. It can be between any endpoints. So you have this infinitary operation, which is like an iterated version of the binary operation, little m, which is the midpoint operation. actually the axioms as Martín originally presented them, you don't need the little m because you can define it using this axiom here from the infinitary m, but it's sort of a little bit more conceptually natural to also have the binary midpoint axiom. And so those are the equations that Martín had. One of them was added slightly later than when we first started talking about it. The most interesting one is I think the third one, of which the bottom one is the infinitary generalization of the third one. So it's like this is the little midpoint operation commutes with itself, and this is the infinitary midpoint operation commutes with itself. And it says if you've got any points, the third one, if you've got any 4 points, so X, Y, Z, W, and you take, this has a very geometric flavor, you take the midpoint between X and Y and the midpoint between Z and W and find the midpoint of those two midpoints. Then if I've drawn the picture nicely, which I haven't, anyway, you know, that's a straight line, and the midpoint works out, and this works for any 4 points, so kind of any quadrilateral. And only a few days ago, Martín sent me some links. Somebody had sent him to some 18th century theorem that you can visualize this because whenever you have a quadrilateral, if you link the midpoints, you always get a parallelogram.
Can you like make the diagrams on the other wall? I can't see it.
I'm sorry, it doesn't matter. You can look at the paper that I'm going to reference in 2 slides' time, and you will see the diagram there.
And also, I had another question. This characterization of the interval as using the midpoints, wasn't this first done by Peter Freyd? Or
no. So let me get on to what we did. So this was what we started with, and it was Martín's interval because he brought it from Imperial and into Scotland, but then we worked on it together. And the main theorems we had were, well, that was an equational axiomatization. We actually needed, for our paper, we needed to have some non-equational principles. There was an important one called iterativity that I don't have time to explain in this talk. But there's also cancellation involved, which is easy to say. And in fact, cancellation implies iterativity. So when you have cancellation, you don't need to have iterativity as a separate property. And the theorems were that if we have cancellation, the free cancellative midpoint operator in the category of sets is the closed interval. And it works in topological spaces, also categories of computable maps. So I didn't put those explicitly on the side, but it works in topological spaces with the right topology, which is what it was designed to do. And the theorem that I was really happiest with at the time, but now writing it out, so I thought I'd write it out in full. It looks pretty horrible. So if you look at an arbitrary elementary topos with natural numbers object, then the free cancellative super midpoint algebra is, well, you can think of it as the Cauchy completion of the rationals. The problem is that the set of Cauchy sequences modulo equivalence, if you don't have either countable choice or what would else be sufficient, what would otherwise be sufficient, the law of excluded middle, but in general, that the set of Cauchy sequences is not Cauchy complete. But you can Cauchy complete that, and one way of Cauchy completing it is to look at the smallest Cauchy complete subset of the Dedekind interval that contains the rationals. Anyway, so those were our theorems, and we submitted them in a paper to LIX 2001. And I think enough time has passed that I can talk about the sorts of things one shouldn't talk about, like referee reports. So we had a very interesting experience at this LIX conference. So we had one referee report in a very strong Austrian accent that so in those days, the grades were from 0 to 6. It gave a grade of 6 and said in the report, if he or she could, then they would give a mark of 7. But we also got a mark of 1. So there must have been an interesting program committee discussion. In the end, we had the experience, our paper was accepted, but we were shepherded. It's my only ever experience of having a paper shepherded at a conference. So shepherded merely means that you have someone from the program committee helping you to address the concerns of the program committee. So in this case, we then submitted the paper under shepherding, which I think in both of our opinion ended up making the submitted paper, the published paper, worse than the original submitted version. So anyway, it was obviously a slightly controversial acceptance from the viewpoint of the conference, but then they invited us to submit the full version to the conference special issue. But that was going to be in the Computer Science Journal, and we thought maybe we'd like to make the paper a bit more mathematical. So we decided not to submit the paper for the special issue. We thought we'll write it up in our own terms. But the problem with that was then we didn't have a deadline to work to. And so this paper did not get written for a very long time. We worked on it immediately after the LIX conference for a period of a year or so. I mean, we were doing other things as well, of course. We came back to it in the early teens of the teens of the 21st century. And we were finally kicked into action by an inquiry from Paul Levy, who's in the audience here a couple of years ago, saying, you on this slide here from some talk back in 2011, you claimed this. Did you ever write it up? So Martin and I, a couple of years ago, started meeting every Friday afternoon on Zoom, over Zoom for an hour a week, and we actually finished the journal version of our paper, and we have submitted it to a journal. So if it gets accepted, which is a big if, then we're competing for the record of the longest gap ever between conference paper and published journal version of the paper. Well, we'll see if it even gets accepted. I mean, I bet there's longer gaps. But there might be longer gaps. Anyway, who knows? Okay, so how long do I have left? I seem to.
About 4 minutes.
Right. So what I want to do is raise some open questions related to our work. We didn't resolve everything. So for our characterization of the interval, even in the category of classical category of sets, is non-equational. So one should just be able to get it equationally, and you shouldn't have to, cancellativity should be a property, should be a consequence of freeness. And actually, we've got a conjecture in the journal version of the paper that a certain additional flattening axiom is sufficient to get that characterization, but we didn't work through the details. So if somebody would like to prove that, that would be great. The bigger problem is, this Cauchy completion of the Cauchy reals is not really what you want in a topos. The Dedekind reals are much more natural. I mean, Lorvier was not very happy with our paper, I know, because, so for example, in sheaves over topological spaces, we're characterizing the wrong interval object. So it would be nice to have a way of characterizing the Dedekind interval in an arbitrary elementary topos with natural numbers object that actually gets the Dedekind interval. So Peter Fried, relating to the question, does have a way of doing that. But the axioms are very different from ours. It's about sort of being able to join two intervals together. I mean, midpoints also play a role, but there's some co-inductive characterization involved in some operation that joins in a logically quite tricky way two intervals together. And what's not clear in that work is the universal property doesn't seem to have any computational content. So our approach, the really good thing about it is it has some computational content. So between our conference paper and the journal version, the submitted journal version, there's another midpoint, which is in between. We did actually write another paper on this, in which we used our universal property to extend a type theory, system T, with primitives related to the universal property. So you have the endpoints of the interval, which I'm now going to change to -1 and 1. The constants in the, so you add an system T is simply type lambda calculus with the natural numbers. We add a type for the interval. We add the infinitary midpoint, the finite one, the infinitary one, and an affine map, something called AF, which is basically the universal property that is the free interval, which gives you, if you've got any two endpoints in the interval, you get an affine map from the interval that you start with into the interval that goes to those endpoints. Anyway, that's equationally there, but for time reasons, I'm going to skip that. It turns out that with those primitives that come from the universal property, there's no closed term that represents the truncated doubling function on the interval. So multiplying by 2 and then truncating it at the endpoints. So it's natural to add that. And the main theorem of that paper was that if we consider this extension to system T with the abstract interval and those universal property inspired constants and the double function, then what you can define in a purely extensional way using those primitives coincides with exactly what is programmable in ordinary system T with or as functions between the real numbers if you use the type natural numbers to natural numbers as a way of representing real numbers via signed binary sequences. So that's a kind of a nice theorem that we're exactly characterizing, in a sense, the primitive recursive functionals over the interval. And a nice little problem that we thought was an interesting problem at the time, but we didn't work on, and it would be nice for somebody to do this, would be to get a similar theorem to hold just for a context of primitive, so without the function types over. So just, you know, in our original LIX paper, we had a notion of what we called primitive interval function. And maybe the primitive interval functions enjoy some similar property that they're exactly the functions codable in a certain sense using primitive recursion, although you have to be a bit careful because in primitive recursion you don't have the function type, so you have to formulate things carefully, which is one of the reasons we haven't really taken time to look at this problem. Yeah, but I think my time is finished, so this is one problem. And then there's the real line, which we didn't include anything about the real line in the paper because we disagreed about how to do it, and we disagreed with ourselves as well. We never found, but there was one suggestion in that intermediate paper, the TLCA paper from 2014, and I just wanted to raise the question there that there's an interesting thing if you represent real numbers using a mantissa exponent representation where the mantissa is given by this abstract interval, then it seems that for all the functions we've considered, it seems that you don't need this double function anymore in order to program real number functions on the mantissa interval. And there should be a theorem there, but it's a question because I don't even want to make a conjecture. Okay, so sorry for rushing at the end. Thank you for your attention. Thank you, Martin, for years of enjoyable company and very, very stimulating discussions, and congratulations on your 60th birthday.
Thank you.
Probably one question. So Steve has,
Can you say anything about iterativity? Because when Martin introduced me to
I missed super midpoint algebras altogether and just thought iterativity was the condition.
yeah, because maybe super midpoint. Sorry.
Turn it off.
Maybe super midpoint wasn't very emphasized in the original paper, but it's emphasized much more in the 2024 version. So probably what you did was in between.
Okay.
Yeah. I mean, iterativity follows from super midpoint plus cancellation. But yeah, iterativity is an interesting principle in its own right, but I don't want to. I want to spend time to say what to do.
Yeah, I thought it was important for me.
Yeah. No, it is an important principle. It didn't fit into this talk. I mean, which was already too long. Okay, let's thank our speaker again. Martin's two eldest children, when they were younger. They're a bit older now. That is canal.